Imagine for a moment learning an entirely new skill,
Right.
but not by, meticulously following some step-by-step instruction manual.
Mm.
Instead, you're just trying things out, seeing what works, maybe getting a little bit better with each attempt.
Like trial and error.
Exactly, trial and error. And you're intuitively adjusting your approach based on that, like, immediate feedback. It feels like a very human way of learning, doesn't it?
It really does, yeah.
Well, that precise process, the trial and error, the continuous feedback, the adaptive improvement, that's actually at the very core of one of AI's most powerful and frankly rapidly evolving paradigms, reinforcement learning, usually just called RL.
Indeed. And welcome back, everyone. Today, we're embarking on a truly fascinating deep dive into this world of reinforcement learning.
Yeah, let's get into it.
Our mission today is pretty clear. We want to unpack its fundamental concepts, explore how this cutting-edge approach is really revolutionizing everything. I mean, from the intricate process of training sophisticated reasoning models.
Which we hear so much about.
Absolutely. All the way to optimizing these huge, sprawling global supply chains and even streamlining complex serverless computing environments. It's really broad.
Wow. Okay.
And we'll be distilling some, pretty dense technical details. We've looked at a wide array of sources, academic research papers, university course transcripts, even comprehensive market analysis reports.
Right.
And the goal is to turn all that into clear, actionable insights for you.
So by the end of this deep dive, hopefully you'll have a much better handle on just how fundamentally RL is reshaping the future of AI and, its potential impact on your world.
That's the plan.
Okay, let's get straight into it then. All right, let's unpack this at its most fundamental level. What exactly is reinforcement learning? We mentioned it's like learning by trial and error. So can we picture maybe a digital agent, which is just, an AI program at its simplest, learning directly within an environment. It does something, takes an action, and then it immediately gets feedback. And this feedback, it comes as a reward if the action was good, beneficial, something like that.
Yeah, or maybe a penalty if it wasn't. Or sometimes just nothing. No reward for a neutral action.
Okay. And the agent's goal isn't just to get one reward, right? It's trying to figure out the best sequence of actions over time to maximize the total reward it gets, the cumulative reward.
That's it, exactly. Machine learning through self-discovery.
Self-discovery, I like that.
And that's really the profound beauty of RL, I think, and where it fundamentally diverges from other big machine learning paradigms like supervised learning.
Right, supervised needs all those labels.
Precisely. Supervised learning absolutely requires this huge collection of inputs that are painstakingly paired with their correct outputs. You need the answer key, basically.
Yeah.
RL, on the other hand, it thrives on this self-discovery and optimization, especially in environments that are dynamic, uncertain, where it would be just impossible or totally impractical to pre-label every single situation the agent might possibly run into.
Like driving a car or playing a complex game.
Exactly. Think about navigating a complex city you've never been to, or playing chess or Go. You can't possibly label every single potential move as good or bad beforehand. You learn by playing, by trying things, and getting feedback. Did you win? Did you get closer to your goal?
Makes sense.
So the agent's entire learning process, its evolving understanding of what counts as good behavior or an optimal strategy, it's derived solely and continuously from this reward system and its direct interactions within that environment.
Okay, so back to that classic rat and maze analogy people often use. Our digital rat, it doesn't get a map beforehand.
Nope.
Instead, if it takes a step, maybe turns right, and that brings it closer to the cheese, the exit, it gets a positive reward, a little point.
Yeah, a little virtual pat on the back.
Okay. And if it turns left and hits a dead end or moves further away, maybe no reward. Or even a small negative score, a penalty.
Could be either. Depends on how you design it. But yeah, that's the feedback loop.
And this seemingly simple loop action, reward, adjust, that's the powerful mechanism. That's how it learns over time which actions are actually useful for reaching its goal.
That's the core of it. It's not told the map of the maze. It effectively builds its own understanding, its own internal representation or value map of the maze by exploring, figuring out which paths tend to lead to rewards, and reinforcing those successful movements.
And critically, it's not just memorizing right turn here was good. It's building a strategy, right? Like turning towards open spaces seems generally better.
Exactly. And that strategy, that's what we call the policy in RL terms.
Yeah.
The agent's current way of behaving.
Gotcha. Policy.
And, the apparent simplicity of this core idea, learn by doing, optimize for future rewards, it often belies the immense complexity and, frankly, the ingenuity of the algorithms underneath. But that fundamental idea, it stays constant no matter how complex the problem gets. It's powerful because it mirrors, in a way, how biological intelligence seems to learn.
Okay. So, to really understand how this learning by doing works for an AI, we need to break down the key components of an RL system. First up, you mentioned the reward function.
Mm-hmm. Crucial.
When we say reward, it's not always just about a simple correct or incorrect answer, is it? That feels too simplistic for complex tasks. It must be more nuanced.
You've absolutely hit on a critical point there. While correctness is often a core component, yeah, especially in tasks with objective right answers like, say, math problems.
Sure.
A reward function is actually designed to evaluate goodness across multiple dimensions, sometimes very subtle ones.
Like what? Give me an example.
Okay, consider an AI model generating text like a summary or an answer to a question. Goodness could certainly include factual correctness, yes.
Right.
But it can also include efficiency. Did it give the answer in fewer, more concise words?
Yeah.
Was it efficient? Or fluency and coherence, does the output flow naturally? Does it avoid weird tangents or, disjointed language?
Okay, so readability, conciseness.
Exactly. And crucially, especially for models interacting directly with humans, it can even reflect more subjective preferences, like, was the response kind? Was it helpful? Did it match a particular stylistic tone we wanted?
Ah, so you can bake in personality almost.
In a way, yes. So the reward function acts like a sophisticated scoring system. It essentially assigns a numerical score to an output or an action across all these different dimensions that you, as the system designer, actually want to optimize for in the model's behavior. It's not just pass-fail. Think of it like a detailed rubric grading an essay.
That makes sense. It's about shaping the behavior in a much more nuanced way across a whole spectrum of desirable traits. But that must make designing these reward functions incredibly tricky.
Oh, it is. It's one of the hardest parts of RL in practice.
Because if you get it wrong, the AI could optimize for something completely bizarre that technically gets a high score but isn't what you actually intended.
Precisely. That's the reward hacking problem we'll definitely touch on later. It leads perfectly into the next key component, policy optimization.
Right. You mentioned earlier the policy is basically the model itself, its strategy for deciding what to do. So what does optimizing that policy actually involve? What's happening under the hood?
Okay, so yeah, in the context of something like a large language model, policy is essentially the model's internal configuration, that vast network of weights and its specific architectural design. It's the agent's current brain, if you like, dictating its actions or responses based on the situation.
Okay.
Policy optimization, then, is the continuous iterative process of adjusting those internal weights and parameters. The whole goal is to make the model consistently generate actions or responses that get more reward in the future.
Like tuning an instrument,
Yeah.
making small tweaks to get the right notes.
That's a great analogy.
Mhm.
You're constantly making small adjustments to make it play tune the optimal behavior more accurately and reliably. Now, there are many specific algorithms for doing this: PPO, A2C, DQN, lots of acronyms. But the fundamental goal of all policy optimization techniques is always the same. Iteratively refine the model's policy so it learns to consistently earn more cumulative rewards over time, nudging it closer and closer to that desired optimal behavior.
And this is where things can get really interesting technique-wise. We saw a specific one highlighted in the sources, Group Relative Policy Optimization, or GRPO.
Ah, yes, GRPO.
Most optimization methods seem to look at one action, get a reward, update. But GRPO does something different, something more relative. What makes it special?
Right. So GRPO introduces a really key nuance and aligns very well, actually, with how humans often learn and refine their own problem-solving approaches.
How so?
Instead of just evaluating a single action or a single response in isolation, GRPO looks at multiple possible actions or responses the model could take at a given step. And crucially, it scores them relative to each other.
Multiple options compared side by side.
Exactly. This group relative comparison provides a much richer learning signal, I think.
Okay, can you give a concrete example? Make that clear. Maybe with that reasoning problem you mentioned earlier.
Absolutely. Let's take that classic problem. How many gumballs fit in a basketball?
Okay.
An LLM trying to solve this might generate several different lines of reasoning, different approaches to tackle it.
Right, different ways to think it through.
One approach might simplify things drastically, maybe estimating the basketball's volume by treating it as a cube, easier math, but less accurate.
Sure.
Another approach might take the time to estimate it more properly as a sphere using the correct volume formula. That's a better approximation, geometrically speaking.
Okay, makes sense.
Now, with GRPO, instead of just giving a final score based on the numerical answer, or even just evaluating each thought process on its own, the system explicitly compares these different approaches side by side. It can then learn that estimating the volume as a sphere is relatively better than estimating it as a cube, because it aligns more closely with desired, more accurate reasoning principles, even if, initially, both approaches lead to an incorrect final number.
So it's learning how to think better, not just whether the final answer was right.
Precisely. This group comparison really mimics how humans might look at different ways to solve a problem. We recognize superior methodologies, not just correct answers. It's about learning the quality of the thinking process itself relative to other possible processes.
That is a powerful way to guide learning, focusing on the methodology, not just the endpoints. So putting all these pieces together, the agent, the environment, the reward function, the policy optimization. How does this all come together in practice? What does the overall RL training loop actually look like?
Yeah, it's an iterative loop, as we've kind of implied. It goes like this. You start with the current version of your model that's your current policy, phase 1. You let this policy interact with its environment. You observe the actions it takes, the responses it generates. Think of it as the agent just playing or acting in its world. Step 1, act. Step 2, evaluate. You take those actions and responses and feed them through your carefully designed reward function. This assigns those numerical scores based on how good they were across all your defined dimensions. Correctness, efficiency, coherence, whatever you've decided matters. That's the feedback step.
Step 2, get score.
Step 3, learn. Based on the rewards received or the penalties incurred, you update the model's internal weights and parameters. This update is specifically designed to make behaviors that led to higher rewards more likely in the future, and behaviors that led to lower rewards less likely.
Step 3, adjust strategy.
Exactly. And then you repeat. You go back to step 1 with the updated model, let it act again, evaluate again, learn again, over and over in continuous iterations.
A cycle.
A continuous feedback cycle. And hopefully, with each loop, the model's policy gets refined, and its actions become progressively better at maximizing those cumulative rewards in the long run. It's constantly adjusting and improving, striving towards that optimal strategy.
And crucially, this loop naturally involves that tension between exploration and exploitation, doesn't it?
Ah, yes. The classic dilemma.
The agent has to sometimes try new, randomish things to discover potentially better strategies it doesn't know about yet. That's exploration.
Right. Got to try new restaurants sometimes.
But it also needs to use the good strategies it's already found to actually get rewards. That's exploitation.
Exactly. Stick with your favorite dish if you know it's good.
So how does the RL system balance that? It seems fundamental.
It's absolutely fundamental. It's
Yeah.
one of the core trade-offs baked into RL.
Right.
If an agent only exploits, it might get stuck doing something that's okay, but not the best possible, a local optimum.
Right.
If it only explores, it just thrashes around trying random stuff and never actually gets good at anything, wastes time and resources.
So the algorithms have ways to manage this.
Yes, the reward function design and the policy optimization algorithms themselves often have built-in mechanisms to manage this balance. Things like epsilon greedy strategies, where it mostly exploits but takes a random action a small percentage of the time, or more sophisticated methods using uncertainty estimation. The goal is always to encourage just enough exploration to discover better strategies while ensuring it effectively leverages the best behaviors it's learned so far. It's a key design consideration for any real-world RL application.
Okay, let's shift gears a bit now. One of the really exciting, maybe even transformative applications of RL is in training reasoning models. We hear that term a lot. How do they fundamentally differ from the standard large language models, the GPTs and Geminis most of us interact with?
Yeah, this is a really critical distinction, and it often gets a bit blurred in popular discussion. A true reasoning model, or at least the goal is, introduces an explicit thinking process, like an internal monologue or a chain of logical steps before it gives you the final answer.
So it shows its work, almost.
Kind of, yeah. It breaks down the problem, processes information step by step, follows logical rules internally. Traditional LLMs, on the other hand, are typically trained using supervised learning, specifically on that task called next token prediction.
Right, predicting the next word.
Exactly. If you ask a standard LLM to fill in a blank like the sky is blank, it primarily relies on statistical likelihood. What word most often follows the sky is the mountains of text it was trained on. It's about grammatical correctness, fluency, mimicking patterns,
But not necessarily deep understanding.
not necessarily deep logical problem solving in the way we think of reasoning. It's brilliant at language, but that's different from multi-step deduction.
Okay, so for a math problem then, like if 2x plus 3 equals 9, what is x plus 5? A traditional LLM wouldn't actually solve the algebra.
Probably not in the way a human would. It might get the right answer sometimes, especially if it's seen similar problems, but it would likely try to predict the answer based on patterns it's memorized, like what numbers typically appear after x, or in similar equations. It's not usually isolating x, substituting, calculating.
It's pattern matching, not algebraic manipulation.
Exactly. It's not typically understanding the underlying algebraic logic, or working backward, or evaluating the correctness of intermediate steps like 2x6 and x equals 3. That's precisely why traditional LLMs often struggle with complex, multi-step math or nuanced logical reasoning tasks when relying purely on next token prediction. They lack that robust internal thought process mechanism.
Okay, that makes the difference clearer. So how does reinforcement learning change the game? How does it enable this kind of depth or internal reasoning in AI models?
RL provides a really crucial, almost profound advantage here. It allows us to evaluate the entire problem-solving process, including all those intermediate reasoning steps the model takes, not just the final answer it spits out.
Oh, okay, so you're not just grading the final number, you're grading the showing your work part too.
Precisely. With RL, you can give rewards not just for getting the ultimate right answer, but for the quality of the thought process itself. Was it logical? Was it coherent? Was it efficient? You're directly encouraging the model to develop and follow sound internal reasoning pathways, rather than just guessing or repeating memorized outputs.
Okay, let's make that concrete. For a math model solving a word problem, how would you actually reward the thinking steps?
Right. So using RL, the model might generate different potential solution pathways, what we sometimes call thought blocks or chains of thought.
Sure.
For each line or step within its generated think block, you could have a reward model assess. Is this step mathematically accurate? Does it logically follow from the previous step? Is the overall process concise, or did it go off on unnecessary tangents?
So partial credit for good steps.
Exactly. Partial credit for good thinking. The rewards aren't just for getting, say, 550 gumballs as the final answer in that earlier example. They're also for how the model reasoned its way to 550 gumballs.
And that's powerful because
Because feedback can be given much earlier and more specifically. If a thought path goes wrong at an intermediate step, maybe a calculation error or a logical flaw, the model gets immediate negative feedback for that specific step. This allows it to potentially correct its reasoning trajectory midstream, rather than just finishing with a wrong answer and not knowing where it went wrong.
it's like having a tutor looking over your shoulder at every single step.
It's a perfect analogy, a very patient, very fast tutor.
Okay. And what about the data you use to train these reasoning models with RL? How are reasoning data sets different from the massive web scrapes used for standard LLMs?
That's another key difference. Unlike those truly enormous, often unstructured data sets used for next token prediction.
Billions and billions of words.
Trillions, sometimes. RL for reasoning often works with more structured data. This data might explicitly provide the desired thought process alongside the problem and solution, often in a step-by-step format. Think of textbook examples with worked-out solutions.
So the data itself contains examples of good reasoning.
Sometimes, yes. But what's even more innovative and common in modern approaches like RLHF, reinforcement learning from human feedback,
Right.
is that during training, the model actually generates its own reasoning data. It explores different solutions, different thought pathways, and then a separate reward model, which itself might be a sophisticated AI trained on human preferences or ratings, scores these holistic outputs. It scores the entire thought process and the final answer.
So the model learns by generating possibilities, and another model tells it which ones are good.
Essentially, yes. This iterative generate and score loop allows for continuous optimization across multiple criteria like correctness, logical flow, conciseness right from the start. It helps the model internalize robust reasoning strategies, not just memorize facts or patterns.
Okay. Now, we saw some practical, maybe simplified examples of this in the university course materials you looked at. Let's touch on a couple of those to make this really concrete.
Absolutely. Let's start with the rather illustrative movie hater example.
A movie hater.
Yeah, sounds a bit funny. The goal here was to train a small G2T2 model to simply review movies negatively. The dataset was just prompts asking for movie reviews. And the initial reward function was super simple. Just a basic sentiment analysis model. Positive sentiment, bad reward. Negative sentiment, good reward.
Okay. Seems straightforward enough. What happened?
Well, a key learning, and this is a recurring, sometimes frustrating challenge in RL, was the phenomenon of reward hacking.
Reward hacking. Okay, that sounds like the model found a cheat code. It figured out how to get the reward without actually doing what you wanted it to do, which was write a real negative review.
Precisely. The model, being a relentless optimizer, discovered that if it just repeated phrases like not working properly or the script is bad over and over again, it would consistently trigger the negative sentiment classifier and get a high reward. Even if the resulting text was complete nonsense, totally irrelevant to the movie prompt or grammatically terrible.
So it learned to game the system.
Exactly. And this example, though simple, starkly reveals a core difficulty in RL. The real challenge isn't just coding the algorithm, it's accurately translating complex human intent, write a thoughtful negative review, into a quantifiable reward function that an algorithm can't easily exploit.
Because the AI will always find the path of least resistance to maximize that numerical score.
Always. Even if that path looks utterly bizarre or useless from a human perspective, it forces us to be incredibly precise about defining good behavior in a way the machine can't misinterpret. Designing a robust reward function is really an art and a science.
So it needs to be much more complex than just, is sentiment negative?
Oh, absolutely. In practice, a good reward function for something like that might need to check for repetitiveness, maybe measure coherence, perhaps even verify that it mentions actual plot points or characters from the movie prompt. It often involves multiple components, or might even be another sophisticated neural network trained specifically to provide nuanced, multi-dimensional feedback that's harder to game.
It's surprisingly hard to quantify good for an AI. That's a really powerful takeaway.
It truly is. Now, we also looked at a math reasoning application. Here, the goal was more complex. Train a model to solve grade school word problems.
Okay, like the two trains leaving the station type.
Exactly. And the data set for this was carefully structured. It included not just the final numerical answer, but also the complete step-by-step thought process, the chain of reasoning that led to that answer.
So for this kind of problem, how is the reward function design approached? You'd want to encourage both the right final answer and a logical thinking process, right? While trying to avoid that reward hacking issue.
Right. So to tackle that, the reward function used a more layered approach. It gave some points, some partial reward for each mathematically accurate line within the think block the model generated.
Okay.
So if the model correctly identified a necessary subproblem or performed a correct intermediate calculation, like 2x equals 6, it received a small reward for that specific line.
Rewarding the step.
Rewarding the correct steps. And then additionally, a larger cumulative reward was given if the final answer was also correct.
So it incentivizes both good thinking along the way and getting the final result right.
That was the intention, yes. Balancing the process and the outcome.
Even with that more sophisticated layered design where there's still practical challenges, it sounds like you're aiming for a perfect system, which is tough.
Oh, absolutely. Challenges remain. Even with this layered reward structure, reward hacking is still a potential risk. Well, imagine a model figuring out it can just repeat a few simple, correct mathematical statements over and over, like 1 + 1 = 2, within its thought block, to rack up those line-by-line points, even if those statements aren't relevant to solving the actual word problem.
Ah, okay. Gaming the partial credit.
Exactly. It highlights that constant, delicate balance you need between rewarding individual steps and ensuring the overall solution makes sense and actually answers the question. You might need further tweaks, like normalizing the line rewards by the total number of lines, or adding penalties for excessive repetition or irrelevance. It's an ongoing refinement process.
Makes sense.
And beyond the subtleties of reward design, the sheer computational cost for this kind of training really stood out in the materials.
Right. You mentioned RL can be intensive.
Extremely.
Huh?
Even for relatively small models like the GPT-2 used in these examples, and even with access to high-end GPUs, which are pretty much essential for this deep learning work, a single full training run for the math reasoning task could take many hours, often 9 hours or more, based on the logs.
9 hours for one run on a small model. Wow.
Yeah. It really underlines the substantial GPU memory requirements and the significant time investment demanded by deep reinforcement learning, even in these controlled academic examples. Scaling this up to larger models and more complex, open-ended reasoning tasks, well, the computational needs become astronomical. It's a major practical constraint.
That computational cost is definitely a hurdle, but it also hints at the sheer complexity and, I guess, the power that's involved here. Okay, so moving beyond training these really sophisticated reasoning models, where else is reinforcement learning making significant waves? We're hearing a lot of buzz around the idea of agentic AI. How does RL fit into that vision?
Agentic AI. Yeah, that term is gaining a lot of traction, and it represents a really significant conceptual leap forward in AI capabilities, I think.
How would you define it?
It's about moving beyond AI systems that just passively respond to prompts or queries. Agentic AI refers to systems capable of more self-directed decision-making. They can set goals, make plans, continuously learn, adapt to changing circumstances, and proactively interact with their environments, often without needing constant human handholding.
So more autonomous, more proactive.
Exactly. And RL is absolutely fundamental to this whole paradigm. It integrates really deeply with advanced concepts from decision theory, planning, and autonomous reasoning. These agentic systems are designed from the ground up to exhibit truly goal-oriented behavior. They learn from past experiences, successes and failures, make adaptive decisions in real time, and dynamically navigate highly complex, often unpredictable environments.
Can you give some examples of things that feel agentic?
Well, classic examples include things like DeepMind's AlphaGo, which learned to master the incredibly complex game of Go purely through RL-driven self-play. That felt very agentic. But we're also seeing hints of it in the latest generation of large models, like GPT-4 or Google's Gemini. They're starting to exhibit behaviors like generalizing complex tasks they weren't explicitly trained on, making multi-step plans, and even learning to use external tools, calculators, search engines, code interpreters in sophisticated ways to achieve goals. They're moving from just being smart responders towards becoming more like intelligent doers.
That does sound like a fundamental shift. So, taking this idea of RL-powered agents and proactive systems, what does this look like on the ground? Can you give us some concrete, real-world examples of how RL is actively transforming industries right now?
Oh, the impact is already immense, and the projections are just staggering. Some market analyses, like the ones we looked at, project the global market for RL technologies could potentially grow to over $32 trillion by 2037. It's a huge number, obviously speculative, but it reflects the perceived potential.
32 trillion. Wow. Okay, so where is this value coming from?
Its applications are incredibly diverse. They're really permeating almost every sector imaginable. Let's start with robotics.
Okay, robots learning on their own.
Exactly. RL enables machines to learn complex physical behaviors directly through interaction, much like how a baby learns to walk by trying, falling, adjusting, trying again.
So, less explicit programming of every joint movement.
Far less. This ranges from achieving highly stable locomotion for quadruped robots, allowing them to walk, run, and climb over varied and uneven terrains.
Like those Boston Dynamics videos.
Precisely. Those are often showcases of advanced control, sometimes involving RL. It also applies to precise drone navigation, enabling autonomous flight for tasks like complex obstacle avoidance, infrastructure inspection, or target tracking in cluttered environments. And even incredibly dexterous object manipulation, like teaching a multi-fingered robotic hand to grasp and manipulate irregularly shaped objects it's never seen before.
That sounds really hard.
It is. Companies like Swiss Smile, mentioned in the sources, are building these advanced wheeled-legged robots, kind of hybrids, that cleverly integrate both RL and supervised learning to adapt autonomously in unstructured outdoor environments.
Combining learning methods.
Yes. And a really notable example we saw was OpenAI's earlier work with a robotic hand. They successfully used a technique called domain randomization.
What's that?
It means training the robot intensely in simulation, but constantly randomly changing parameters of that simulation. Things like friction on surfaces, lighting conditions, the weight or texture of objects.
So making the simulation messy and unpredictable.
Exactly. By training across this wide range of randomized simulations, the policy learned becomes much more robust. It learns to handle variations. And crucially, this allowed them to transfer the complex manipulation policies learned entirely in simulation directly to the real robotic hand, which could then perform surprisingly dexterous tasks.
Ah, so it bridges the gap between simulation and reality.
Precisely. It helps overcome that notorious sim-to-real gap, which has always been a major hurdle in robotics. Models trained in pristine simulations often fail badly when faced with the messy, unpredictable physics and sensor noise of the real world. Domain randomization is one key technique RL uses to tackle this. It's a huge step towards robots that are truly adaptable and robust in the wild.
That is a huge step. Okay, what about autonomous systems, things like self-driving cars or maybe even rockets? How is RL involved there?
Critically involved. Tesla, for instance, explicitly states they employ RL within their autopilot system. It helps with real-time decision-making, incredibly complex and dynamic driving scenarios, things like navigating intersections, merging lanes, anticipating the behavior of other human drivers, which is notoriously hard to predict.
Right, humans are messy.
Very. And SpaceX famously has utilized RL alongside other control techniques to significantly improve the precision and reliability of landing their reusable rocket boosters. That's a feat of incredible control engineering, requiring millisecond adjustments in a highly uncertain atmospheric environment. RL helps optimize those control policies,
Landing a skyscraper on a dime, basically.
pretty much. And then you have companies like Wave and Waymo really pushing the boundaries of autonomous driving. Their RL-powered systems, often trained on vast amounts of driving data and simulation, are frequently shown to outperform traditional, more rigid, rule-based approaches, especially in handling unexpected edge cases on the road.
And it goes beyond just cars.
Yes, the technology extends beyond individual vehicles. There's research and application in optimizing broader citywide systems, like synchronizing traffic signals dynamically based on real-time flow, using RL to try and reduce overall congestion and improve urban mobility on a larger scale. Smart cities, essentially.
Optimizing complex interconnected systems. That seems to be a real sweet spot for RL. How about something as intricate as global supply chain optimization? That feels like another area ripe for dynamic learning.
You are absolutely right. This is a huge area. Here, RL often now combined synergistically with generative AI or Gen AI.
Interesting combo. How does that work?
Well, RL agents are deployed to learn how to adaptively manage inventory levels and make replenishment decisions across these complex, multi-layered supply chains, from manufacturers to distributors to retailers. They learn optimal policies in environments where demand and supply are constantly fluctuating, often unpredictably.
So the RL part handles the decision making. Where does Gen AI come in?
The Gen AI part, using models like GANs or VAEs, is often used to simulate diverse and realistic demand scenarios for training the RL agent. It can generate synthetic but plausible future demand patterns, including rare but high-impact events like sudden surges, disruptions from natural disasters, or competitor actions. Things that might not be well represented in historical data alone.
So Gen AI creates realistic what-if scenarios for the RL agent to train on.
Exactly. It provides richer, more robust, and more varied training data, especially for handling uncertainty and rare events. This combined approach has been shown to significantly improve key supply chain metrics, reducing stockouts, improving inventory turnover efficiency, lowering transportation costs. It's really about moving supply chain management away from static periodic optimization based on forecasts,
Which are often wrong.
which are often wrong, exactly towards continuous, feedback-driven adaptive coordination across the entire network.
That sounds incredibly powerful for businesses. Okay, what about a domain that feels quite different? Serverless computing, cloud functions, things like AWS Lambda. How does RL fit in there?
Yeah, this is a fascinating and increasingly critical application that really highlights RL's versatility. It's being used to tackle a core operational challenge in serverless platforms, efficient task scheduling.
Scheduling which function runs when and where.
Precisely. Traditional scheduling methods in these environments often struggle because the workloads can be incredibly bursty and unpredictable. And they suffer from that cold start problem, a delay, when a function hasn't been used recently and needs to be spun up.
Right, those cold starts can kill performance.
They really can. So researchers have developed sophisticated RL frameworks. These frameworks learn from vast amounts of real-world logs of function indications, when functions were called, how long they took, what resources they needed. Based on this data, the RL agent learns to make dynamic, optimal scheduling decisions.
What kind of decisions, like where to place the next function call?
Exactly. Which server to run it on, whether to keep certain function instances warm proactively based on predicted future demand. And the results are impressive. Studies cited in the sources show these RL-based schedulers can reduce average function latency by up to 30% compared to traditional, more static methods. And they significantly mitigate those costly cold starts through more intelligent, proactive resource allocation. It leads to much more efficient and responsive cloud infrastructure.
Wow, 30% is huge in that world. It's amazing how the same core RL principles learned from interaction, optimized for a reward like low latency, apply across robots, supply chains, and cloud servers.
It really is. The underlying mathematical framework is surprisingly general.
Okay, the sources mentioned a lot of other application areas too. Could you maybe quickly highlight a few more just to give us a broader sense of RL's incredible reach,
Hmm.
perhaps grouping them thematically?
Sure, happy to. The list is long, but we can group them. For instance, there's a lot happening in optimizing complex biological and financial systems.
Okay.
In biotech, RL is being explored for things like optimizing dynamic treatment regimes, tailoring interventions for chronic conditions over time based on patient response. It's also used to accelerate drug discovery, maybe by helping identify promising molecular compounds or predicting drug efficacy. Companies like Biomimetic or Dows and Isomorphic Labs were mentioned as players here.
Adapting treatments on the fly.
Potentially, yes. And in fintech, RL is heavily used in high-frequency trading, HFT, where algorithms make split-second buy-sell decisions. It's also being applied to things like optimizing venture capital investment strategies, trying to predict startup success or optimal funding amounts. Firms like AI Capital Management were cited. The common thread is learning optimal strategies in really dynamic, data-rich, high-stakes environments.
Makes sense for finance. What else?
Then there's a cluster around enhancing critical infrastructure and resource management.
Like power grids.
Exactly. In energy management, RL is used to optimize electricity distribution, predict grid load, maybe plan network maintenance schedules more effectively.
Hmm.
Companies like Enlight AI are developing systems for better energy allocation and even emergency response coordination, aiming for grid stability and efficiency.
Crucial stuff. And
Yeah.
agriculture.
Yeah, in agriculture, RL helps optimize resource use, water, fertilizer, can improve crop yield predictions. And it's enabling automation for tasks like precision spraying, using drones with RL-guided navigation to apply pesticides only where needed, reducing overall usage. Or even robotic harvesting, learning to identify and pick ripe fruit. Green eye technology was mentioned for the precision spraying aspect. It's all about efficiency, sustainability, and sometimes automation in these sectors.
Farming getting high tech with RL. Okay, any other big
And
buckets?
maybe a final big bucket is driving innovation within AI and digital domains themselves.
RL improving AI itself.
Yes, and related fields. In manufacturing, RL is used for things like automating the design of complex components, like printed circuit boards, PCBs. Quilter was mentioned there. It's even assisting in complex scientific research, like optimizing parameters in quantum physics experiments with companies like Cruise.
Designing circuits and running physics experiments.
Wow. In AI R&D more broadly, RL is enhancing software functionality. Axiomatic AI is working on automated interpretable reasoning models, and some companies, like Poolside with their Malibu model, are using RL variants, specifically reinforcement learning, from code execution feedback, RLCEF, to train generative models to write computer code that actually runs correctly and even matches a company's specific coding style.
Learning to code by seeing if the code works.
Essentially, yes. And then there's defense, where RL is increasingly applied to automate high-risk tasks. Think autonomous operation of drones or vehicles in GPS-denied environments. Shield AI was mentioned. Complex drone mission management, RbRL. Or anomaly detection in cybersecurity logs, Cohere Technology Group.
Obvious applications there. Healthcare operations. Marketing.
Yep. In healthcare, beyond drug discovery, RL enhances hospital operations, optimizing patient flow through emergency rooms, allocating resources like beds or staff more efficiently, improving surgical scheduling. Unity AI's platform was cited as an example focused on operational efficiency,
Making hospitals run smoother.
hopefully. And finally, in marketing, RL is used for dynamic decision-making, personalizing content delivery for individual users in real time, optimizing pricing strategies dynamically, even automating A/B testing campaigns to quickly figure out what messaging works best. Companies like Ampy, OfferFit, and Motiva AI are all leveraging RL for things like personalized user experiences or optimizing email campaigns.
So it's personalizing ads and emails too.
Among many other things, the sheer breadth across all these sectors, from farms to finance to physics labs, really underscores just how fundamental and potentially transformative RL is becoming. It's touching almost every aspect of our technologically driven world.
That overview is incredible. It really paints a picture of RL becoming almost foundational technology across so many different fields. But it sounds like despite this breadth, it's still very much an active, rapidly evolving area of research, right?
Oh, absolutely. Very active.
So what are some of the cutting-edge techniques that are pushing the envelope right now? Maybe going beyond the basics we've covered, perhaps trying to address some of the challenges we might anticipate with these increasingly complex systems.
Yeah, researchers are constantly refining how RL agents learn and interact, specifically aiming to overcome current limitations and enable RL to tackle even more complex real-world problems. There are several key directions. One really significant area is hierarchical reinforcement learning, HRL.
Hierarchical, like layers of learning.
Exactly. HRL breaks down really complex, long horizon tasks. Think tasks like assemble this piece of furniture or win this hour-long strategy game into a hierarchy of more manageable sub-goals.
Okay.
You might have a high-level policy that decides, okay, first I need to find the leg pieces. It then delegates that sub-goal to a lower-level policy whose job is just navigate to the box labeled legs and pick them up. That lower-level policy might then delegate even further to policies for specific motor actions like grasp handle.
Breaking big problems into smaller learnable steps.
Precisely. And the big advantage here is sample efficiency. By learning these modular sub-policies, the agent often needs far fewer interactions with the environment to learn a complex overall strategy. This is absolutely crucial in domains like real-time strategy RTS games, where the number of possible action sequences is astronomical, or in robotics, where each real-world interaction can be slow, expensive, or even risky. HRL makes learning feasible in these massive state action spaces.
Makes learning faster and more practical for huge problems.
God.
What else is cutting edge?
Then there's a lot of focus on model-based and offline RL, which are really crucial for practical deployment.
Okay, model-based and offline, what's the difference?
So offline RL is about learning exclusively from pre-recorded static data sets of past interactions. The agent never gets to interact live with the environment during training.
Learning just from logs.
Exactly. This is vital when real-world exploration is dangerous, like training a self-driving car from crash data. You don't want it learning by crashing. Expensive, like running experiments on costly industrial machinery, or just slow. You learn from whatever data you already have.
Makes sense. And model-based.
Model-based RL is different. Here, the agent tries to learn an internal model of how the environment works. It learns the physics or the rules of its world.
It builds its own simulation.
Kind of, yeah. This internal model allows the agent to simulate the likely outcomes of its actions before taking them. It can mentally play out scenarios and plan ahead, which can drastically reduce the amount of real-world trial and error needed. Both offline and model-based approaches aim to reduce the heavy reliance on vast amounts of real-time interactive data collection, making RL more data efficient and safer to deploy.
Very practical considerations. You also mentioned challenges like sparse rewards, where feedback is rare. How is research addressing that?
Right? Sparse rewards are a huge headache. Imagine trying to train a robot to make a cup of coffee. It might only get a reward right at the very end, if the coffee is perfect. All the hundreds of steps before that get no feedback.
So it wanders aimlessly for a long time.
It can, yeah. It struggles to figure out what actions are even remotely useful. So researchers are designing more sophisticated mixed reward schemes and using techniques like curriculum-based reward shaping.
What does that involve?
It might mean starting the agent with easier versions of the task, or providing more frequent, small, intermediate rewards for achieving sub-goals, like picking up the mug, adding water.
Yeah.
Gradually increasing the difficulty, that's the curriculum part. The reward shaping involves carefully designing these intermediate rewards to guide the agent towards the final goal without accidentally creating reward hacks.
Guiding the agent along.
Exactly. Additionally, related techniques like Bayesian uncertainty modeling are becoming more important. These help agents make better decisions when they're unsure about the environment or the outcome of their actions. The agent explicitly tracks its confidence level and can choose to act more cautiously or explore more deliberately when uncertainty is high. It's about making more informed choices under ambiguity.
Thinking about how sure it is. Okay. And one more advanced technique mentioned was dynamic action pruning, especially for games.
Yes. This is particularly relevant in environments with enormous action spaces, like complex strategy games, think StarCraft, where at any given moment, the agent might technically have thousands or even millions of possible actions it could take.
It's like moving any unit anywhere, building anything.
Right. It's computationally infeasible to evaluate all of those options. Dynamic action pruning intelligently filters out actions that are likely to be irrelevant or low impact in the current situation. If 1,000 actions are possible, but maybe only 5 are strategically meaningful right now, the pruning mechanism eliminates the other 995 from consideration for that decision step.
Cutting down the choices drastically.
Exactly. Studies showed this can reduce the computational overhead by something like 35% without significantly harming the agent's strategic performance. This is crucial for enabling these complex RL agents to actually run and make decisions in real time, which is obviously essential for playing games or controlling robots.
making RL feasible for fast-paced, complex decisions. That's really cool. Now, shifting slightly, there's also some really exciting work on how we can make RL even more effective by integrating human insight more deeply, right? Something called RbRL 2.0 came up.
By yes, rating-based reinforcement learning 2.0. This is a fascinating area, really trying to bridge the gap between how machines learn and how humans provide feedback and learn from experience.
Okay, so standard rating-based RbRL, uses human ratings to learn a reward function, right? Humans say, this was good, this was bad.
Correct. It's a common approach in RLHF, for instance. Humans rate different outputs or behaviors from the AI, and those ratings are used to train a reward model, which then guides the policy optimization.
So how does RbRL 2.0 take that further?
RbRL 2.0 tries to mimic how humans learn more effectively, specifically from experiences of varying performance levels. We don't just learn from perfect successes and total failures. We learn a lot from our near misses, our okay but not great attempts, our different kinds of mistakes. We understand degrees of suboptimality.
So it's not just a binary good-bad rating, but learning from the spectrum of not quite right. That sounds like a much richer signal.
It is potentially much richer. The core technical innovation in RbRL 2.0 is a novel policy loss function. This function does something interesting. It penalizes the similarity between the current policy's behavior and behaviors that humans have rated as failed experiences, basically anything not deemed optimal.
Okay, so it pushes the policy away from bad behaviors.
Yes, but here's the crucial twist. It assigns different weights to these penalties based on how badly the experience was rated.
Ah.
Lower-rated experiences, the really bad mistakes, incur a larger push-away force in the loss function. The policy is strongly discouraged from behaving like that. In contrast, higher-rated experiences, those that were still suboptimal but maybe closer to the desired behavior, the near misses get a smaller push-away force.
So it learns, definitely don't do that, but maybe avoid this slightly less.
Exactly. It leverages a much more nuanced understanding of bad performance, moving beyond a simple binary signal. It extracts richer, more directional information from the human feedback, not just wrong, but how wrong, and maybe even implicitly in what way was it wrong. It's almost like teaching the agent what not to do, but with varying degrees of emphasis based on the severity of the mistake.
That feels much more aligned with how we actually learn. What have the results shown? Does this nuanced human feedback translate to better AI learning in practice?
The initial experiments reported in the sources are promising. They tested RbRL 2.0 on standard continuous control benchmarks, simulated tasks like making virtual creatures, half cheetah, walker, quadruped, walk, or run efficiently.
Okay, standard RL testbeds.
Right. And the results show that RbRL 2.0 consistently outperformed previous RbRL methods, especially in the more complex environments like the walker and quadruped tasks. It demonstrated faster learning, reaching higher performance levels with fewer training steps, and achieved higher final cumulative rewards.
So the nuance helps it learn better and faster.
It appears so, at least in these environments. It really highlights the potential value of extracting more detailed directional information from human feedback, going beyond simple preference labels, A is better than B, to incorporating a richer understanding of performance quality.
That's really exciting work. Okay, so even with all these incredible advancements, HRL, offline learning, RbRL 2.0, you mentioned RL, is still relatively nascent in some ways. What are the big, significant remaining challenges that researchers and developers are still actively grappling with? What are the main practical hurdles holding back even wider adoption?
Yeah, despite all the progress and the truly exciting applications, RL definitely still faces some significant hurdles, and researchers are working hard on these. First, and we've touched on this, computational costs.
Still big one.
Huge. Training these deep RL algorithms remains incredibly intensive. That continuous trial and error, often involving complex neural networks, requires vast amounts of computation, typically GPUs, and often very long training times.
Those 9 hours for the simple math problem.
Exactly. And that was a small model. Scaling this to real-world problems with much larger models in state spaces like training a truly general-purpose robot or a comprehensive autonomous driving system demands absolutely astronomical computational resources. The source mentioning Meta having over 350,000 high-end NVIDIA GPUs, partly for AI training, gives you a sense of the scale involved at the cutting edge. This cost is a major barrier for smaller companies, academic labs, or anyone without access to massive compute clusters.
Limits who can play at the frontier. Okay, what else?
Second is data scarcity and quality, particularly real-world interaction data.
Didn't we say RL doesn't need labels like supervised learning?
It doesn't need pre-labeled input-output pairs, true, but it often needs vast amounts of interaction data records of the agent acting in the environment and receiving rewards. Acquiring sufficient high-quality real-world interaction data can be incredibly difficult. Well, for many reasons. Ethical concerns are huge. You can't just let a medical diagnostic AI experiment on real patients or an autonomous car learn by crashing repeatedly. Privacy regulations often limit access to useful data. And sometimes it's just the sheer cost and logistical difficulty of setting up systems to gather that real-world interaction data safely and effectively, especially in sensitive domains like healthcare, finance, or critical infrastructure.
So getting the right kind of experience data is hard.
Very hard. And if the data you do have is sparse, noisy, or biased, the RL agent will struggle to learn a robust and generalizable policy. It might perform poorly when deployed in slightly different real-world conditions. This is why simulation and techniques like offline RL are so important, but they come with their own challenges, like the sim-to-real gap we discussed.
Right. Third challenge.
Third is the persistent difficulty of reward design complexity.
Ah, the reward hacking problem again.
Exactly. As we saw with the simple Moviator example, crafting a reward function that perfectly captures your true objective and effectively guides the agent without opening loopholes for unintended or easily gamed behaviors is extremely difficult. It's a delicate art.
Balancing short-term nudges with a long-term goal.
Yes, and ensuring the reward truly reflects complex human values or objectives. If the reward function isn't meticulously designed and tested, the AI, as an optimizer, will find the easiest, potentially nonsensical path to maximize its score, completely missing the actual point of the task. This often requires deep domain expertise and lots of iterative trial and error in designing the reward itself.
A constant battle against unintended consequences. Okay.
Fourth is generalization issues. RL models often struggle to transfer what they've learned in one specific training environment or simulation to new, unseen environments, or even just slightly different variations of the real-world scenario.
So it learns to drive perfectly in the simulator but fails on a real road with slightly different lighting.
That's the classic problem. Or a robot trained in one factory layout struggles when moved to a slightly different one. This lack of robust generalization means that models often need significant retraining or fine-tuning for each new deployment context, which is costly, time-consuming, and limits scalability. Improving generalization remains a major focus of RL research.
Makes deployment harder. And finally,
A really critical one, lack of explainability.
the black box problem.
Exactly. Many sophisticated deep reinforcement learning architectures, especially those using deep neural networks, operate largely as black boxes. It can be incredibly difficult, often impossible, to truly understand why the AI made a particular decision or took a specific sequence of actions, especially in complex, high-dimensional environments.
You see the output, but not the reasoning behind it.
Precisely. And this is a critical bottleneck, particularly for adoption and high-stakes applications. Think autonomous systems, medical diagnosis, financial trading, defense applications. In these areas, trust, accountability, the ability to debug failures, and regulatory compliance are paramount. If you can't explain why the AI did what it did, especially when it fails, it's very hard to certify it as safe or reliable.
Limits trust and deployment in critical areas.
Absolutely. So addressing these formidable challenges, the compute costs, the data needs, the reward design intricacies, the generalization gap, and the explainability deficit is really paramount for RL to unlock its full, truly transformative potential across all the industries we've discussed.
That point about explainability is particularly fascinating, isn't it? If an RL agent makes a critical mistake in a car, in a hospital, and we genuinely can't understand why it made that choice, that fundamentally limits its deployment in areas where safety and trust are non-negotiable. It really makes you wonder what kind of new research frontiers will open up just to tackle that specific black box problem within RL itself.
Well, it's a huge and very active area of research, definitely. People are exploring techniques like trying to extract rules from the learned policy, using attention mechanisms to see what the model focused on, or building inherently more interpretable RL models.
Yeah.
But achieving truly human understandable explanations for the complex, emergent behaviors of sophisticated RL policies. That's still one of the grand challenges in AI today. It likely requires foundational breakthroughs in AI interpretability methods, not just tweaks to existing RL algorithms. Hashtag outro.
Wow, what an incredible deep dive into reinforcement learning. We've really journeyed from the fundamental mechanics, that intuitive process of trial, error, feedback, and reward.
A core loop.
Exactly. All the way through. It's truly groundbreaking applications, training AI models that can actually reason, revolutionizing robotics and autonomous systems, optimizing these incredibly complex global supply chains, and even streamlining the backbone of cloud computing with serverless optimization.
And we also touched on some of the cutting-edge research that's pushing the boundaries even further. Things like hierarchical RL for tackling massive problems, model-based and offline RL for practicality, and fascinating approaches like RbRL 2.0 that try to incorporate human intuition more deeply into the learning process.
RL really does feel like an undeniably transformative force in AI. It's enabling systems to learn autonomously, to adapt to constantly changing environments, and to optimize for really complex objectives in ways that, frankly, traditional programming or even other types of AI often struggle with.
Absolutely. It's unlocking new levels of intelligence and automation, it seems, across nearly every industry you can think of, from biotech and finance, as we discussed, all the way to energy, agriculture, manufacturing, defense. It's incredibly broad.
But as we just covered, while the potential is immense, those challenges remain significant. The computational cost, the need for good data, the difficulty of designing robust rewards, ensuring models generalize, and crucially, that challenge of explainability. These are still major hurdles.
They are. But the ongoing innovations we've talked about today, the new algorithms, the new techniques, the new ways of incorporating human feedback, they are steadily making RL more robust, more efficient, and increasingly applicable and deployable in the real world. The pace of advancement is just, well, it's breathtaking, honestly.
It really is. So as reinforcement learning continues its rapid ascent, it kind of leaves us to ponder, doesn't it? What new kinds of truly intelligent agents will emerge from this paradigm of continuous learning and adaptation? And how will they fundamentally change the way we interact with technology, or maybe even how we approach solving some of humanity's most complex technical challenges?
Yeah, and how might our daily lives be subtly yet profoundly reshaped by these systems that are constantly learning and optimizing in the background, making decisions that weren't explicitly programmed by a human, but were discovered through dynamic interaction with data and the world? The possibilities, when you really think about it, seem truly boundless.
A fascinating thought to end on. And for those of you who want to dive even deeper into the specifics, perhaps look at some of the research papers we drew from for this discussion. You can always visit our webpage. The link is in the bio, where we often list sources and further reading.
Definitely worth checking out if you want to get into the technical weeds.
We hope you found this deep dive valuable, and we hope you'll join us for our next one.